Okay, so I want to look at this problem where we have this equation x cubed plus y cubed equals 6y. And we want to answer a couple of questions. One is find the equation of the tangent line at the point 3, 3. And then another is find the point in the first quadrant where the curve has a horizontal tangent. Now, this might look very ugly to you because we have an equation in x and y where it's not very easy to solve for x or y. And there's a good reason for that. And so for that reason, I want to actually take a look at the graph. So I'm going to use Desmos to look at the graph. So here's what the graph looks like. This is called the Folium of Descartes. Descartes was a mathematician and philosopher. You might know him from the famous utterance, "I think, therefore I am." His name is also connected to this coordinate system we have, which is called the Cartesian coordinate system. Cartesian, named after Descartes. Anyhow, also folium means leaf. So this is the leaf of Descartes. So you might know the word foliage as plants that have leaves. So this is in the section 3.5 on implicit differentiation. And I think that you have heard by now that in implicit differentiation, we look at some equation in x and y, and we say that y is defined implicitly as a function of x. And I'll be honest with you, I have struggled with understanding that meaning for, I still continue to struggle with understanding that meaning, and I kind of have this grasp on it. But it's been very hard for me to think of how to pass on this grasp to students. And in some sense, my grasp on it has been, I don't know. It's like part of my understanding of it is that it's not that important that I understand it too deeply. But something occurred to me today that I think that I've never seen anybody mention, and I think it's important to mention. So this curve that is defined by this equation, y is not a function of x, and x is not a function of y. The curve intersects itself. It has, multiple x values for the same y value. It has multiple y values for the same x value. But if you think about a point moving along this curve, then the x values and y values must change in some way that relates to each other, okay? So if I think about just altering the x coordinate, if I somehow take this point and I want to drag it back and forth, just changing the x coordinate, there is no way that I can do that without also changing the y coordinate if I want to stay on the curve. And similarly, if I want to change the y coordinate, then if I drag it in that direction, in order to stay on the curve, it must also change the x coordinate. So the x coordinate and the y coordinate are dependent upon each other, okay? So this is one way in which it makes sense to say, even though y is not a function of x, there is a dependency of the y coordinate on the x coordinate. Okay, that if you change the x coordinate, that will force a particular change in the y coordinate as well, and vice versa. And so this is another way to think of what it means that, there is an implied function relationship here. And so when we differentiate this, we will not be able to solve y as a function of x, because clearly y is not a function of x, okay? But we can talk about the derivative of y with respect to x. And I want to ask that question. So I addressed this question of what does it mean that y is defined implicitly as a function of x. And I want to ask this question, what does dy dx mean? And really what this is, it's so funny how when I was in college, it was really taught to me that dy dx, this notation, was not meant to be a fraction notation or a ratio notation. But the more I have learned, the more I've learned that it really is. This is a ratio of the change in y to the change in x. That d is meant to be a change. It's a difference. Okay. So what is the ratio of change in y to change in x? And once I understand that, like, if I choose to change the x coordinate, then the y coordinate must also change. So y is dependent on x. It is also true that if I choose to change the y coordinate, then the x coordinate must change. So x is dependent upon y. X and y are intricately linked through this equation, okay, or through this curve. So dy dx is a ratio of the change in y over change in x. In this particular point, in this area, I can think about the ratio of the change in y to the change in x, and the change in y looks like it's very close to the change in x at this point. Over here, if I change x quite a bit, y doesn't change very much. So the change in y divided by the change in x in this area would be a small number, and it would be a small positive number. Up here, if I change x just a tiny bit, that will change y quite a bit. So my change in y divided by change in x would be a larger number. And we are accustomed to thinking of change in y divided by change in x as being a slope. And so we can talk about this, the slope of this tangent line here would be a large positive number. So that's one of the things we could think about is, the derivative of y with respect to x is a ratio of how much change y has versus how much change x has in some small region around that point. Okay, so the questions we were asked to answer were, what is the equation of the tangent line at the point 3, 3? I'm going to put up that point 3, 3 for a visual now. Okay, there's the point 3, 3. And I'll ask you to take a minute and see if you can guess what the tangent line is at that point. I'm going to guess that the slope of the tangent line is probably -1. This looks very much, and if I zoom out, this curve looks very symmetric. And I can see from the equation that it must be symmetric, because if I exchange the x and the y coordinates, then I get exactly the same equation. If I trade x for y, I get the exact same equation. That means this equation, this function must actually be symmetric across the line y equals x. Okay, because y equals x is the line of symmetry when you exchange x and y coordinates. So this means if it's completely symmetric across that line, then the tangent line has to have a slope of -1 at that point. Okay, so we could actually write that basically just based on symmetry. The slope, a slope of -1 passing through the point 3, 3. But we're going to use the implicit differentiation tool that we have to practice that. The other question we had was, at what point in the first quadrant does the curve have a horizontal tangent? Okay. And so we can actually drag this point up and guess. It looks like it's somewhere around there. Like I think I'm seeing the highest y value here is somewhere around there. So x is 2.528 and y is 3.175-ish. If I was to zoom in a little bit further, I don't know how much more precise I could get just by playing with this point. But that is something that we're definitely going to have some use some calculations to discover. All right, so let's go and go back to the notepad to practice to do the calculations. So this equation does involve a relationship between x and y, and so we can work with the equation assuming that that y is a function of x. So what I can do with this is I basically just take the derivative with respect to x of every single term in this equation. Now the derivative with respect to x cubed, we use the power rule, so this is 3x squared. Now the derivative with respect to x of y cubed, y is dependent upon x, okay? If x changes, then y must also change too. So we have to use the chain rule for this because y is a function of x. So we first differentiate this expression with respect to y, which is 3y squared. And then we have to multiply by the derivative of y with respect to x. The derivative of y with respect to x. That is the chain rule. Okay? Equals. Now, taking the derivative of this other side, well, I can write the 6 is a scalar on the outside. And then the derivative of x times y, I need to use the product rule. So I have x times the derivative of y. So that's x times the derivative of y with respect to x, plus y times the derivative of x with respect to x. Okay, what is the derivative of x with respect to x? That is 1. I do notice at this point that I have a factor of 3 on every single term, so I'm going to divide by 3, divide this whole equation by 3, and I have x squared plus y squared times dy dx equals, and this is now a 2, and I'm going to distribute that through. This is 2x times dy dx plus 2y. Now, my goal here is to find some expression for dy dx. So I want to move all of the dy dx terms to one side and solve for dy dx. So I'm going to move this term over here and move this term over there. So I have y squared dy dx minus 2x dy dx equals 2y minus x squared. This is y squared minus 2x all multiplied by dy dx equals 2y minus x squared. So dy dx equals 2y minus x squared divided by y squared minus 2x. All right, so again, my formula for the derivative of y with respect to x, this is the ratio of change in y to change in x, is going to be a function that involves both x and y coordinates. This is necessary because the x coordinate does not define where the y coordinate will be, right? The x coordinate 1 has 3 different y coordinates on this graph. So it is necessary to put in both the x coordinate and the y coordinate in order to determine what part of the graph you are on. So our charge here was to find the tangent line at the point 3, 3. So let's take this and go up here. The derivative of y with respect to x at the point 3, 3 is 2 times y is 3 minus x is 3, so 3 squared, divided by y squared, that's 3 squared, minus 2 times x is 3. And you can see the numerator and denominator are the exact same terms but opposite signs, so that is going to be -1. So I have a line with a slope of -1, as I predicted. The slope is -1, and it passes through 3, 3. So the equation of the line would be y equals -1 times x minus 3 plus 3. Or if you felt like simplifying this would be y equals -x plus 6. All right, so that is the equation of the tangent line through the point 3, 3. Let's look at what is the point in the first quadrant where the curve has a horizontal tangent. And we saw in Desmos that it was, let me see if I can find it. We saw that it was around 2.5 and 3.2. Around 2.5 and 3.2 is the place where there is a horizontal tangent there. So let's see what we can do with the calculations. So the point in the first quadrant where the curve has a horizontal tangent. So we want to look at dy dx equals 2y minus x squared divided by y squared minus 2x. And a horizontal tangent means that we will have the dy dx equals 0. Now we have a quotient, we have a fraction basically. The only way to have a fraction equal to 0 is if the numerator is 0. Technically, if the numerator is 0 and the denominator is not 0. Now, there is an interesting thing about limits happening here that I will try to remember to address when I go back to the graph on Desmos. But in order to have dy dx equals 0, at the very least, we have to have that numerator equal to 0. So this is where 2y minus x squared equals 0. So we can solve this for y and say y equals x squared divided by 2. Now this is a condition for dy dx to be equal to 0. And this might not seem like enough information. So it is important to remember that we also have a condition that the point xy has to be on the curve. So we also have to have the condition met where x cubed plus y cubed equals 6y. This is telling us that xy is on the curve. So putting these two pieces together, we have a way to solve an equation. We can make an equation to solve. So let's actually substitute y equals x squared over 2 into this defining equation for the curve. So I'm going to put this in for y there, and oops, I made a mistake. This is x cubed plus y cubed equals 6xy. And now I can say I want to put this also in for y there. So now I have x cubed plus x squared divided by 2 all cubed equals 6x times x squared divided by 2. So this is x cubed plus x to the 6th divided by 8 equals 3x cubed. Okay, let's subtract the 3x cubed from both sides, and I have x to the 6th divided by 8 minus 2x cubed equals 0. I'm going to multiply everything by 8, so I have x to the 6th minus 16x cubed equals 0. factor out an x cubed. That gives me x cubed minus 16 equals 0. That tells me that x to the third power equals 0, or x equals the cube root of 16. Okay, let's evaluate this. If x cubed equals 0, now looking back at the piece where y equals x squared divided by 2, this would give us that y equals 0. So if x cubed equals 0, then that means also x equals 0. If x equals the cube root of 16, let me actually write this up here. So now, if x cubed equals 0, that also tells us that x equals 0. And we'll use that y equals x squared divided by 2. So that would tell us that y would also equal 0. Now, if x equals the cubed root of 16, that has an 8 in it. So that's the cube root of 8 times the cube root of 2. That's x equals 2 times the cube root of 2. So y would equal the square of that divided by 2. So it would be 4 times the cube root of 4 divided by 2, which is 2 times the cube root of 4. So in this case here, it would be the point 0, 0. And in this case here, it would be the point 2 cube root of 2 and 2 times the cube root of 4. And this is approximately 2.52 as the x-coordinate, and 2 times the cube root of 4 is approximately 3.17. Okay, and those are close to the coordinates that we found just by fishing around by dragging a point on the graph. All right, and I want to take a look at this 0, 0. You can see that 0, 0 does in fact have a horizontal tangent, but it also has a vertical tangent, depending on which part of the graph you're coming in at. But then the other horizontal tangent is here, where the x-coordinate is 2.52 and the y-coordinate is 3.17. All right, I want to go back to the graph. So let's actually put that point in here, so it's 2 times the cube root of 2. There's the 2.52, and 2 times the cube root of 4, and there that is. There's my coordinates. Let me take my draggable point out of there. Okay, so that, the horizontal tangent, of course, would be just y equals 2 times the cube root of 4. Okay, and that would be the horizontal tangent line. If we zoom way in there, we can see, yes, that does look like the right tangent line. Okay, and one of the things that I kind of want to point out is that this, the formula, if you'll remember, for the derivative dy dx was 2y minus x squared divided by y squared minus 2x. Okay, now if you put in x and y are both equal to 0, if you put in the origin here, then you will get a 0 divided by 0. It's undefined. And And so in order to figure out what the derivative would be, you would have to take a limit as x and y both tend towards 0. And the funny thing is about this, we're not going to go into the depths of this, but I just kind of want to give you a little bit of a clue as to what's happening here. Like taking a path where x and y are both going towards 0, it kind of depends on which way you're coming in at. So if I'm coming in on this path, then my dy dx, the slope of my tangent line, looks very much like it's going towards 0. Okay, and you can see it's a little bit unstable there. So my dy dx is going toward, like the slope of the tangent line is going towards 0. But if I come in on this part of the path and I'm coming in here, I'm still approaching x and y approaching 0, but my derivative formula at this point is going to tend towards positive infinity. Okay? And even worse, if I come in from this point, my derivative is going to tend towards negative infinity. Okay? So this is a Calc 3 sort of thing. But, we have seen, looking at limits and seeing what the limit is if we come at this value from the left or from the right, and, determining the limit requires that both the left-hand limit and the right-hand limit go to the same number. And in this case, where I have two variables that are moving, I want both x and y to move towards 0. There's a lot of different paths that I can come in at. And one thing that we haven't addressed is that, I could come in from some completely other angle. And so, this is a little argument that this expression does not have a limit as x and y go towards 0, because it's very dependent on what path you take going in towards 0. 0, 0. Okay, so this is just a little bit of an aside and kind of a touching on the complexity of how limits work when you are working with kind of bigger pictures. All right, so there is that problem of calculating the slope of the tangent line at 3, 3, and then also finding the point in the first quadrant where the tangent line is horizontal. And a little bit of the pointing out the complexity of this limit as x and y approaches 0, 0 kind of tells you why the book really only asked to find the point in the first quadrant where there's a vertical tangent. In the first quadrant where there is a horizontal tangent. And this was not asked in the book, but I think it's a good exercise. At what point in the first quadrant does the curve have a vertical tangent? Okay. But they basically skipped over the complexity of what's happening at 0, 0 because we don't have the tools to approach that yet. Okay, and it's interesting if you play with this graph, you will even notice that there's a sensitivity to me dragging the point. Like I can drag the point along that part of the curve if I stay really close. But if I let my cursor kind of go off at all, it will jump off here and I am stuck on the vertical part of that curve. So there's there's a funny sensitivity to what's happening on this curve at the place where it intersects itself. All right, time to end there and move on to the next thing.